Can you all hear me okay? Yep. Okay. Yeah, today I'm going to talk about weak supervision. But before I start the presentation, I have to thank my team who did most of the research on this project. So I've just done like the classic manager technique of delegating the work, and now I'm taking all the glory by presenting it as my own work. So I've got to thank my team for the hard work. So who am I? As my introduction said, I'm currently Director of Machine Learning at Ravlin. Ravlin's a fraud detection company. We have about 5 data scientists, 5 analysts, and some engineers and other supporting staff that all work on the machine learning side. Ravlin's a fraud detection company. We detect various kinds of financial crimes. Before that, I was at a fashion company called List, also running the data science team. And before that, I was doing my PhD in an obscure, useless branch of maths. So, frauds. There are many types of fraud, many types of financial crimes. The kind of financial crimes that we care about are mostly crimes that affect merchants. So the interesting thing about the financial payment system, there are a couple of interesting things about it, surprisingly, is that when you buy something on the internet with a credit card, the banks and the schemes have wrangled it so that they are no longer responsible for fraud if the credit card doesn't exist in person. It's down to the merchant instead. So we work with merchants to protect them from attacks against this sort of thing. So we mainly work, card not present, which is online transactions, but there's also a bunch of other types of fraud, like when people's accounts get hacked or when the actual sellers are defrauding. We've had situations where people create fake restaurants and order to the fake restaurant and make money that way. Or also things like friendly fraud, where you as a consumer ring up your credit card company and pretend you've been defrauded to get the money back and get the goods for free. So all sorts of different types of fraud for that. Now, I probably don't need to talk to a room of data scientists about how important labels are, but they're incredibly important to us and quite hard to collect. And I know it's the same in many other domains, or they can be expensive or even like ethically objectionable to collect. But the biggest jumps in machine learning we've seen in the past years is all thanks to new labeled data sets. So if you look at something like ImageNet is responsible for the massive jumps we saw in image processing using CNNs and deep learning and that sort of stuff. And if we didn't have a good labeled data set, we wouldn't have been able to make the progress we did. So let me talk a bit about fraud labels. So the main label we have in fraud is called a chargeback. That's when you ring up your bank and say, I didn't make this transaction. Then the bank tells, your bank tells the scheme, which is Visa. Visa tells the merchant tells us. So you have this really long cycle. It can take anywhere between like 2 weeks and 4 months for us to get a chargeback on a transaction. So the labels are really high quality, but they're really slow to get to us. So I mean, that raises some problems for us, because if we train a model and we want to deploy it and we want to be really sure that this model is going to detect frauds, we're really training on data that's 4 months old, and then we're using that model on data that's recent. So you have to put in loads of work to make sure you don't deploy a broken model. And I think there's been quite a few presentations at this PyData all about how to be sure the model you're deploying is good. So I'm happy to see more people that are thinking about that. Another big problem with chargebacks, and one of the reasons we're looking into weak supervision, is the better we do as a company and the better we do for our clients, the fewer labels we get, because each person we detect as fraudulent, we block from transacting, and then so we do not get a chargeback for them. And we can end up in this situation where we get very, very few chargebacks. Those chargebacks are for really hard cases of fraud. So we end up overfitting on these really hard cases, and the model almost forgets about the easy cases, and we start letting easy ones through again. So it's really important we can somehow add common sense to our model, even if we're not getting active labels about these common sense data points. And that's another thing weak supervision can do for us. So there are good labels. we also have many, many other sources of labels of dubious quality. And it'd be really awesome if we could somehow use these dubious quality labels to inform our model and sort of remove ourselves from being fully reliant on chargebacks. So some sources of dubious labels would be, say, manual reviews from our clients. So clients go into our dashboard and manually say, this is fraud, this isn't. Sometimes those reviews are really amazing. Sometimes those reviews are really terrible, and it just exposes the biases of the person doing the review. And many other sources. We have other things. We have rules, we have networks, we have similarity methods, we have something called 3DS feedback. That's when the bank asks you to put your password in when you buy something online. So we have all these different sources, but none of them are good enough to use as a true supervised label. So that's where weak supervision comes in. So one way we can think of weak supervision is putting into this hierarchy of sort of machine learning techniques. You know, typically with supervised learning, we have some high quality labels, or as high as possible. And we don't really do anything with low quality labels. We just exploit the things we really know are good labels. Then you have something in the middle, semi-supervised learning. Semi-supervised learning, we use all our good labels, and then we use our good labels to label unlabeled data. So we're basically exploiting sort of similarity and structural characteristics of the features, and like continuity on manifolds and all those sorts of proximity-based methods to propagate labels to our unlabeled cases. And this works quite well, but you're limited in the sort of things you're going to be labeling. And then there's weakly supervised, where we can make use of our high quality labels and our low quality labels. So made this little diagram before I explain exactly what it is. So you see, in the supervised case, we're just taking the things we really know about. In the semi-supervised, we take the things we really know about and then add a little bit more on that are close to our good labels. In the weakly supervised case, we're sort of just shotgunning the whole instance space with potential labels. I'm going to talk about how we do that. One thing I should say about fraud and why this is useful to us, we really only have negative labels. We only know that someone is a fraudster when we get a chargeback for them. And people who don't have a chargeback, we can't say they're good people. They might also be fraudsters, but we just don't have a signal saying they're fraudsters. We have no like explicit positive signals. So for us, this sort of setup makes quite a lot of sense, where we only care about our fraudulent negative labels, and this area is sort of unknown, and we sort of assume they're good people, but they might not be. Another way we can think of weak supervision is sort of in the hierarchy of machine learning techniques over time, right? So in the 70s, when AI was AI and not like a marketing term, we had like expert systems where people entered a load of rules into a database, and this was AI, right? And the rules triggered, and we like gave a diagnosis to a patient or something. And that was expert systems, where you're engineering the actual decision functions. Then we have sort of the 90s, where machine learning starts coming up, and there we're automating the decision functions, but manually engineering the features. Then we sort of more recently, we've got the deep techniques coming up, where we're not engineering the decision function, we're not engineering the features, we're engineering the architecture of the model and automating the previous forms of things that we were engineering. And then you can think of weak supervision as the next step, where we're now engineering the labels themselves, and a lot of the work could be in constructing the labels we're training on in a sensible way. Which sounds a bit strange, right? Because labels are a universal truth. We shouldn't be engineering them. But weak supervision proposes some methods that we can use to do that. So how does it work? Well, I've got this very confusing diagram from the weak supervision paper. Oh yeah, I should say that most of the work on recent work on weak supervision is all from the group that makes the tool called Snorkel. It's a Python library to do weak supervised learning. Their site's amazing. They're extremely prolific. There's so many papers and blog posts on this. I'll give you the address later. But this is a picture from the Snorkel site. And as an overview at how weak supervision works, your training data you treat as normal, but you generate your labels by taking a lot of weak sources. So here, they've got, NLP taggers. You could just have rules on your text that say, does the text contain angry? Okay, we think the sentiment is negative. You can just add these really loose rules that you could never add as a true label because they aren't precise enough, but you can create all these weak sources here. So it's kind of also, you can think of it a bit like an ensemble, but instead of ensembling model decisions, we're ensembling labels. And basically those go into another model, a generative model, which optimizes not using labels, and it produces a probabilistic label that goes into our traditional machine learning model with our traditional features. So that's a general way it works. So what do our labeling functions look like? They're pretty simple. They take in an instance, so one feature vector or one sentence or whatever the input to your model is, and they return one of three values. -1 if you think there's evidence for your label, whatever you're detecting. In our case, it would be fraud. 1 if there's no evidence for what you think is fraud. And then 0 if there's no evidence. So in the no evidence case for us, it could be, we might have a rule that says, does the user have more than 5 credit cards in one day? That would be a suspicious signal, but it might not necessarily be fraud. They could be a genuine user. So we would say -1 if they have more than 5 cards, 1 if they have less than 5 cards, and perhaps we would return 0 if they've never added a card because they haven't had the opportunity to prove or disprove their guilt yet because they haven't done anything. So you can return 0 in that case. So the idea is you come up with loads of these labeling functions of this form. So some examples of other things you can do. So rules is a very typical one. Can also take labels from humans, which are notoriously unreliable depending on the human. We use graph methods. You can use similarity methods like semi-supervised learning. You can use model predictions from worse models. And the new version of Snorkel, which hasn't come out yet, but it's even got support for things like perturbating feature vectors, transforming data inputs to automatically generate new labeling functions. So, for example, if you think of something like image data, you can't really do rules on image data. It would be very tricky unless you have some extra metadata. So one of the examples that they use in a paper is they segment objects and tag those objects from an image, and then they do rules on the segmented metadata. But it also has support for transformations, so you can do stuff like write labeling functions that just like shear or crop or rotate images to add regularization and that sort of stuff. That's it mostly. And the idea is once you train the label model, you should end up with something like this. So we start with our labels we're really, really sure about, and these we sort of don't really know about. Then we come up with all these labeling functions that tag various things as fraudulent, labeling functions like we've just talked about. And then once you've learnt the model, hopefully your probabilistic label that your generative model comes out with looks something like this. So instead of just having our tiny dot, which is effectively like a probability 1 label for the confidence we have in that label, we end up with this spectrum of labels across from 0 to 1 about how suspicious this person looks based on a combination of all the labeling functions we have. So this is the paper that describes how the generative model works. I read it yesterday, and my intentions were to have a really good explanation for exactly how it worked, but it's quite complicated, and the notation is quite confusing, I think. But the nice summary for it is essentially it's like a correlation-aware generative probabilistic model that learns a latent variable, which is the probability that that instance is fraudulent. And the input is just all your labeling functions for that instance, and your output is just the probability, like the latent factor it's learning. And it uses factor graphs. But if you want to know more, feel free to read this paper. And if you figure out exactly how it works, please come and talk to me. That would be very useful. So that's the generative component that generates our probabilistic labels. The other component is just the discriminative model. That can be anything you want. It doesn't have to be a deep model, but all the literature and at Ravlin, we're using deep models. The reason being that whatever model you use, it has to be able to support a probabilistic label. So something like a random forest isn't going to work. All the literature and Ravlin, the loss of these discriminative models is normally log loss or binary cross entropy, as it's called in many deep learning frameworks. The reason being that, you know, for this loss, this y can be a 1 or 0 and the loss works. This y can also just be a probability and the loss works exactly the same. So most literature so far is using this sort of loss. Okay, so is it any good? So we gave this a test on some of our data. We came up with, I think it was maybe about 20 labeling functions, which isn't so many. And then we trained it and saw how it did. So when we tried it out, we got about 2% additional recall with, 20 labeling functions. And for us, 2% recall is actually really good because most of our models are extremely mature, good at exploiting all the low-hanging fruits. So a 2% recall increase is pretty decent. The other thing to think about with this technique is one of the big advantages is if you don't have any labels, right? We have labels already that are good, but if you have 0 labels and you create a model that actually works well, then your increase in performance is going to be, you know, an infinite increase, right? From 0 to something, right? It's going to be massive. So if you've got no labels, there's a good technique to consider. But there's something a bit strange about it that you need to think about. So here we said we've got a 2% increase in recall, but we can only measure this because we have labels we know about, right? We have good labels already. Like, there's a problem. How do you evaluate your model on your generated labels if you don't already have labels to evaluate on? So that's quite tricky. Depending on your use case, that might be fine. You know, if you're a B2C company and you can deploy to production and track click-through, then you can evaluate based on that. But if you're something like us in fraud, we have to know how well the model performs before we deploy it. So it becomes quite tricky to decide on how do you evaluate this model when you're generating the labels yourself. And surely, one of the reasons we want to generate labels is so we get a broader ability to detect fraud. And if we're evaluating the model on our own labels, are we just optimizing the model to predict the label we already have, right? Are the generated labels actually doing anything useful for us? I mean, that's a question that I haven't answered either, but these are things that came up as we're thinking about it. And another bad case is like, I think weak learning is painted as like this savior technique where you just define some labeling functions, doesn't matter what they are, train a model, everything's brilliant. But like, how do you even define these labeling functions? So if you think of a rule-based approach on a feature vector, you just say, is X bigger than Y, then it counts as a good label for us. That's the sort of labeling functions we have. Do you have more than 5 credit cards, right? But what do you choose for your threshold there? Do you choose like 2 credit cards or 5 or 6? Can you have multiple thresholds, multiple labeling functions that have all sorts of different thresholds? It's really hard to decide. And when we talked about this, we said, well, why don't we just optimize our thresholds based on our chargebacks, based on our true labels? But this is a terrible idea as well, because in that case, you've basically created a really bad random forest, right? You've created just some rules with some splits, and then you're optimizing the splits, and it's a terrible random forest. So why don't we just train a random forest instead and forget about all this? So, I mean, there's some questions I have, basically. And I'm not against Snorkel at all. We're still trying to figure out what's the best way to do this. I think at the moment there's a lot of work on the theory and a lot of high-level case studies, but there's not much work on sort of best practices, and that's what we're trying to figure out at the moment. Another problem we have, well, it's not a problem, is we know we have a really good label, but we can't incorporate that into the model because the current framework doesn't support basically different classes of labeling functions, saying one is more important than the other. But there is a blog post on Snorkel that vaguely mentions something that's coming, and it's actually pretty simple how they do it. They just split their network into two branches, put the important labeling functions in one, the unimportant ones in the other, optimize, learn them separately, mix them together with a weight. So you can sort of approximate it that way. They're talking about it in terms of NLP here, but if you weren't doing NLP features, you just sort of split it, weight them back together to try and give the ability to have separate weights for different classes of labeling functions. So we'll probably be doing that. Now the really important thing for weak learning is something called this labeling function instant density. And this thing, I think, isn't really highlighted as much in the literature, but this is critical to getting a good weak learning system. So you can imagine this diagram here. So let's say the y-axis is every instance, every feature vector. The x-axis are all our labeling functions. And then each cell is basically, did we return a 0, a 1, or a -1 for that labeling function on that feature vector? And the density of this diagram is incredibly important to the performance of the weak supervision system. So there's a bit, so with this labeling function, there's a bit of a Goldilocks issue. So here's a quote from one of the papers. In the low density setting, i.e. when you don't have many labeling functions per instance, sparsity of labels will mean that there is a limited room for even optimal weighting of the labeling functions to diverge much from the majority vote. So what it's just saying here is if you don't have many labeling functions, it's just going to use majority vote and not even bother to learn a generative model. So this means, you know, if you have two labeling functions, it's just going to say, oh, you both said 1, so we'll say this is a fraudster. We'll say this is a label 1. And I think the problem with that, and that it's not so public, is that if you design your labeling functions like they suggest, which is just like very free and not really worrying about how good they are, and then you have this low density scenario, your labeling functions are basically devolving into traditional supervised labels, right? So if we have this labeling function that says more than 5 credit cards, and we don't have enough labeling functions, that more than 5 credit cards is just going to become a traditional supervised label, and our model is going to suffer for it. So you really need to be able to track this. And then in the upper bound case, it's the same. In the upper bound case, you don't need the generative model. If you have so many labeling functions, you can just do majority weighting, and it's just as good. It's kind of the middle ground where we use a generative model and get the probabilistic label. So this is something you should definitely monitor. If you look in the paper I linked before, they have equations for the lower bound and upper bound of density that you should be looking to sit in between. And here's another, I think this just sums up the questions that still need to be answered with this Snorkel work. So this is a quote from a blog. I'm not going to call out who it is because it's a really good blog and they write really good stuff. But my concern about this is really these two things, you know. These labeling functions do not need to be precise, and we should write many of them. I think there's just a lot of questions around how many do we need to write? Can we build supporting tools to tell us how many we should write? And they do not need to be precise. I think there's lots of questions around balances on precision and recall and what the architecturing of your label function should be like. So if you want to take a deep dive into Snorkel, go to this place. This is their official website. They're constantly posting articles. They're constantly doing blogs, constantly posting papers. There's loads of great information here. I just want to say, like my experience of Snorkel, we're super positive about it. We just think we need to do a bit more work. It could be that we've missed papers or we've missed best practices or anything. If anyone's worked with Snorkel, love to chat with them about their experiences as well. So go to this website if you want the current research? No? Snorkel? Streamline your labeling? See what it's all about? This is the best one. Better efficiency? Better efficiency? No? The results sure are unbreathable. No? Finn. Oh yeah, sorry, one thing. If you like the sound of this, and you like the sound of fighting crime, and you like puns, then we're hiring loads of people at the moment, data scientists, analysts, directors. Thanks. Any questions? Sorry.
Thanks very much. That was really interesting. One question, and you kind of touched on it at the start, talking about bias. How much more complex is explainability where you've made use of weak supervision to train the model?
Yeah, that's interesting. I guess it depends. Yeah, that's quite interesting. I mean, in one way, it gives you more explainability because you know what labeling functions triggered for that customer, so you've got maybe an extra source of explainability. I mean, at Ravlin, most of the explainability we do is very black box, so we don't look inside the model. We, manipulate input and look at the output and see what's happened. So in terms of that, it doesn't really affect the explainability we're doing. But yeah, I think you actually get more explainability through the labeling functions. It's quite interesting. Didn't think about that.
Hi, great talk. My initial thought when you were mentioning that you have the issues where you can't you can't have the labels that have different importances, labeling functions. Can you upsample your labeling functions? Could you just have the same labeling function be there multiple times? We use upsampling now anyway to make things more important, say like a certain country or something like that. But yeah, that's true. You could upsample your labeling functions. Yeah.
Any other questions?
So it's actually two questions. So for regression problems, you more or less just tweak labeling functions to produce some sort of like equation thing, and also do you generate the labeling functions based on domain knowledge? As in, like, say you got a problem and you're not very knowledgeable about it, how do you generate the labeling functions?
Yeah. So on the second question, yeah, I think you have to do it based on domain knowledge. I mean, you could, like we're saying, you could potentially automate it if you have some golden set of labels, but I'm not sure, automatically generate these to maximize some performance metric, but I'm not sure if that's a great idea because you're just replicating your golden set of labels instead. So I think, yeah, you have to do it using domain knowledge and experts, but there's definitely a question of how do you evaluate if that's good. And sorry, what was the first question? Oh, regression. Yeah, I don't actually know. I don't know if it's, I haven't seen anyone use it on a regression problem. I'm not sure what you do for that.
Thank you so much for the talk. You mentioned that you are using graph methods to make a labeling function. Can you talk a little bit more about that?
Sure. So at Ravlin, we have our own graph database, and in that graph database, we connect every customer that we've ever viewed by all their sort of entities. So we say this customer's connected to this customer because they've once shared a phone number or they shared a device and we have a big multi-hop network. And we use that as a true label if a customer, say two customers connected and one of them has a chargeback, we'll treat that as a true supervised label. But we have much more distant relationships like, oh, this customer's connected by 8 hops to a customer with a chargeback. And we wouldn't treat that as a true label because the distance is too far. But we can start treating that as a probabilistic labeling function, or we can say something like, a customer doesn't have a chargeback, but they have 180 devices. That's like, it's not fraud, but it's really suspicious. Why have you got 180 devices, right? So we can start adding stuff like that into the model, like evidence-based approach.
Hey, thanks for the talk. You mentioned that it takes like months for you to get chargeback labels.
Yeah.
How do you verify the performance of your models when you put it online and you make sure that it's not doing anything crazy?
Yeah, I mean, I could probably do a whole presentation on this, and I have, in fact. But it's really tricky. I mean, people have done talks here along similar topics, but we just try and take everything we can from software engineering and apply it to machine learning. We have unit tests that run on the model, but machine learning, not to verify the code works, but to verify the predictions are sensible. We have an automatic report that gets generated for every single trained model that has loads of diagnostics. We look at things like the distribution of score over various features to make sure it's not doing anything crazy. We have dark mode, which I think someone has talked about at this conference already, where we run two models side by side. They both score, only the one result goes to the client, the other result just gets stored, so then we can do analysis on the score distribution, how it changed over time. So you basically have to employ all these heuristics and checks and double checks and loads of analysis each to make sure you're not going to break something. Because it's even worse for us, because if we deploy a bad model, we have to wait 4 months before we know it's bad. Then we take it out, and they've still got 4 months of bad chargebacks coming in. So it's like a horrendous event if that ever happens to us, which it has once.
Very interesting talk. Just a question. So this was applied to a binary classification problem.
Yeah.
If you had a multi-class classification problem, could this be done? Is that too complicated? Don't even bother with it.
So you think like maybe you'd have a probability for each class?
Yes, probably the distribution of the classes.
I think that would be doable. Because at the very least, you could just do one versus all, right, on every binary, and then have n generative models, and you have n but then it wouldn't
normal. What I'm about is the number of decision functions you would need.
Right. Yeah. Yeah. I haven't seen any literature that actually does that, but I think that's more likely than the regression scenario, which I'd have no idea how you do a regression problem like this. Yeah.
Thank you.
Okay, there's no more questions. Please help me thank the speaker again.